السلام عليكم، يعطيكم العافية. هذه حتكون آخر محاضرة إن شاء الله، وموضوع التوبكس حتكون Energy and Power Spectrum Densities. هو موضوع مش جديد عليكم، ولكن تكملة لما تم أخذه من قبل، هو بارسيفال Theorem. والتوبك الآخر حيكون هو Analog to Digital Converter and how to perform sampling and reconstruction of the signal. So we start with the energy spectrum density. طبعا power spectrum density we already have studied in chapter 3, how to find the power spectrum density, okay, for periodic signal, if you remember. And today we will concentrate in energy spectrum density. إذا متذكرين كنا نوجد الانرجي in time domain قبل، وقلنا إنه بالفrequency domain we can find a function. When we integrate it, it will give us the total energy. طيب ما أهمية الانرجي spectrum density؟ Then the energy spectrum density is used to determine energy distribution of an energy signal in the frequency spectrum. يعني you can plot as the x-axis a frequency domain, and here you can have the distribution of the energy. Okay, the distribution of the energy as a function. Then if you are interested in a certain band, let's say this is B1 to B2, you are interested in the energy existing in this band, okay? What you are doing integration of this distribution function, then you find the energy concentrated within this band. هذه هي أهميته. طيب, the power spectrum density as well, okay, is used to determine the power distribution of power signal. ركزوا لي هون power signal or energy signal, okay, in the frequency spectrum. طيب, knowledge of this distribution أهميته is valuable in analysis and design of communication systems and other systems. For example, Parseval, طبعا هذا بيؤدي إلى Parseval theorem. Parseval theorem shows that the energy or power, okay, we already have shown the power, and today we are going to show the energy in time domain remains unchanged in frequency domain, so it's preserved. Okay, so we start with energy spectrum density, ESD. We need to get an expression for the energy spectrum density. So when you integrate it over a period of or a band of frequency, you are getting this energy in that band. So recall that an energy signal, x of t, has a normalized energy given by. This is, you have to refer to chapter 1. This expression we already have worked on it, okay, to find the energy. Now we know that this absolute value can be opened into, or magnetic square can be opened into x of t مضروبة في x of t conjugate. Okay, so x of t multiplied by x of t conjugate. Now we express x of t in terms of its Fourier transform. Okay, or we try to find the Fourier inverse. Okay, by finding the Fourier inverse of x of f. So we can write x of t in terms of x of f as such. This is the Fourier inverse. Okay, so x of t expressed in terms of its Fourier representation, and x conjugate, it is there. All right, now we try to reverse, we can reverse the order of integration. Instead of performing the integral in frequency domain, we try to make it in time domain, then we do it in frequency domain. Okay, so then we can reverse the order of the integration. Okay, by reversing the order of the integration, so we perform the integral with respect to time, and then we do it with respect to the frequency, and we can see that if you just let this one outside and this inside, this outside here, and the time integration will be here. All right, then we can since this was a conjugate, okay, we can take the conjugate outside and substitute instead of that minus j2 by ft. Okay, then continue. We know this expression, okay, is the Fourier transform of x of t. So this expression will give me x of f conjugate. All right, and having here x of f, so the integral will be reduced to this expression. And we notice that this is in time, in frequency domain, while we started from the time domain. All right, continue like that. Okay, then we get this expression, which is energy, can be obtained in time domain. Okay, and also you can obtain it from the Fourier transform expression. And if you remember in chapter 1, I told you how to obtain this function, which we refer to it as g of f, this one. Okay, energy spectrum density. You remember I told you we will, when we reach chapter 4, we will learn how to obtain the power spectral density. So this expression is referred to as Parseval theorems, and we have seen Parseval's theorems in chapter 3 for periodic signals, okay, which relates the power spectral density to the average power in time domain. So we define the energy spectral density, okay, as such, of x of t as such, okay, the absolute value of x of f squared. This will give you the power, the energy spectral density. What do we mean by that? It's a function of frequency. So you can see the distribution of the energy, okay, over the frequency, how it changes. And based on that, you can decide which part you need to pass and which part you need to reject, for example. So it describes the distribution of signal energy over the frequency spectrum, integration of g of f, okay, over all frequency or frequencies from minus infinity to infinity, yield the total normalized energy contained in the signal. However, integration of j of f over a finite range of frequency gives the energy contained in that signal within the range of frequencies represented by the limits of integration. So when you perform the integration, if you take it, let's say from minus p to b of j of f, this will give you the energy contained in this band here in minus p, let's say إلى b. So you decide what, or you know what the energy contained is in this band. Okay, now let's take this example. Consider x of t, e minus at u of t. Consider this energy signal. Okay, we need to determine the energy, and we need to find the energy in a certain band, okay, over a range from minus p to b. So we can either find x of f and use Parseval theorem, all right, by taking the square value and integrate from minus infinity to infinity, or we can do it directly in time domain. We can do it directly in time domain. Which one is easier for you? You can do it. Okay, you choose the easiest way. So we take the square value of this signal, real valued signal, and you just straightforward integration. You will obtain 1 over 2 alpha joule, and we know that alpha should be positive. Okay. Now we need to see the energy distribute, or the energy contained in this band, minus p to b, from minus p to b, from minus p to b. You just take the integral of the energy spectrum density. This is energy spectrum density distribution over this band. How to define the energy spectrum density? Okay, from Fourier transform, we know that the pair, you can just refer to the previous lectures or the tables. The Fourier transform of this x of t will give you this form, this expression, by just performing Fourier transform 1 over alpha j2 plus j2 by f. And we know J of F, it's defined as such. Okay, it's defined as such. So you need to find the magnitude of x of f. Magnitude of x of f, you can do it as such. All right, and you take the square value, or you can multiply x of f with x of f conjugate, and then you will obtain the absolute or magnitude squared, absolute value squared. So in both way you can do it. All right, or you square this one, you will obtain as such this one. Both ways you can get the same result. So this is the energy spectrum density. It's a function of time. It's an even function. You can see it's here since you are doing the square value. All right, so you can plot it. You can easily plot it, and if you need to plot it, you can do it as such. Take this as f. All right, and you take, let's say, f equals 0, then the maximum value will be 1 over alpha square. And as f increases, this will decrease. All right, and if it's negative, it will give you symmetric around the. So this is the power spectrum density. This is the power spectrum density. Okay, we can plot it. All right, now we are interested in the energy contained in the signal in this band when f greater than minus p and b. So to do that, we just integrate over this band, straightforward integration. Since it's symmetric, this function is symmetric, you can just multiply by 2 and take the limits from 0 to b. And with a straightforward, or okay, here we divide with some mathematical manipulation. Here you divide over alpha square, alpha square, alpha square, all the terms. So 2 over alpha squared comes outside, and you are left with this expression. Okay, by doing change of variable for this part, replace it with z, and change the limit of integral, of course, accordingly. You will end up with this. And it's known that from integral tables, this integral for this expression will give you cosine inverse. Will give you, sorry, tan inverse. All right, this expression, the integral of this one will give you tan inverse. All right, and this is Joule. If you know, of course, this is an expression because b is unknown and alpha is unknown. If they are unknown, then you easily you will get a number here. Okay. We have to notice something here. Since this is 1 over second and this 1 over second, here is 2 pi. Then we know that the angle inside the tan inverse should be in radian. Okay, radian. So if you substitute the angle here to find the tan inverse, you have to use radian. We note that as b, look here, as b goes to infinity. So if the band is increased or it's become wider, as b goes to infinity, so the limit of energy as a function of b as b goes to infinity, if b, this one goes to infinity, this will converge, the tan inverse will converge to pi over 2. All right, since it converges to pi over 2, if you multiply it with this one, you will get 1 over 2 alpha, which is the total energy contained in the signal. And we already have found this one in time domain here. So you will get the same result as b become wider and wider. Right. In terms of percentage of energy contained in bandwidth p, وهذا bandwidth p minus p, in terms of percentage to the total energy, you just multiply that energy in this band over the total energy. Okay, I multiplied by 100%. So this is in energy in the band B, and this is the total energy. You multiply it by 100%, so you get this expression. Okay, as an inverse problem may occur when we are asked to find the bandwidth such that 85 or 95 or 99% of energy is preserved. So here we are given B, but you are might asked to find B such that 95% of energy is preserved. Inverse problem. Let's see this example. For example, for the previous example, find B such that 90% of energy is preserved. So it's nothing. You just take, this is J of F. Oh, sorry, this is the expression here. We already have found it here. Okay, you just use it. It's ready. So this is the expression, equal 90%. This was what with percent, this percent with percent removed. So you have 90. So tan inverse of 2 pi beta alpha تساوي 90 pi over 200. So if you need to find tan of this part, but remember this should be in radian. You get this 2 pi beta alpha. Then after taking the radian tan of this theta, you will get 6.28, and immediately B will be this expression. For example, if P equal 4, then if alpha equal 4, then B is equal 4 hertz. Okay, so we decided based on how much energy we need to preserve in the signal. So we decided the bandwidth of the, we can decide the bandwidth of the filter which we design usually. Okay, this is the end of this topic. We'll start now another topic. So the topic will start chapter 8, which is analog to digital conversion. It's an important topic, and this is the intermediate point between the time domain signal and, between continuous time signal and discrete time signal. Now, a computer system usually needs information to be presented in the form of numbers, and then from the numbers to digital, okay, digital number. So having continuous time signal is not useful for to be processed in the computer, okay, or to be stored. So these numbers or samples, we refer to them here, representing some information or signals, need storage capacity. So you need storage capacity for these numbers or for these samples. Now, storage capacity, we know that it is finite, it's infinite, because already we have seen that if you need to store a continuous time signal, you need an infinite infinite capacity. And this is not acceptable. So storage capacity is finite. So signals can only be sampled. You cannot store the whole signal. You need to sample it. Okay, you need to sample it for a finite time. All right. So you can store it, you can process it, and so on. So the main issue comes here, okay, is to what extent should we sample these signals? Are we free in doing sampling, in taking sample from this signal? Are we free or not? Or is there any limit for doing sampling? Or what is the limit for the sampling rate? So that important features, we do sampling, so that important features of the signal are not lost by sampling. So there is a trade-off. You do sampling, at the same time, you don't need to lose the important information, okay, or features in this signal. So we need to answer to this question, okay? How many samples should we take per second, of course, per second? How many samples should we take per second so that we don't lose, okay, the signal important features, okay? Now let's introduce the block diagram of analog to digital converter. Usually we pass the signal x of t to low pass filter, and later on I will show you why we pass it to low pass filter to be band limited signal, to make it band limited signal. However, this is not important for the time being. So let's say you have x of t immediately comes to the sampler. And you know, before going to the sampler, you have analog input signal. What do we mean by analog input signal? Analog, it means it is continuous in time and continuous in amplitude. When it comes into the sampler, it changed to, it plays with one parameter, either with the time, okay, or with the amplitude. So the sampler changed the time. So it changes from continuous time into discrete time, while the amplitude is still continuous. Still, we need to do more step, which we will pass the signal to the quantizer, and this quantizer will change the continuous amplitude into a discrete as well. So the signal now, it is in discrete time and discrete amplitude, okay? Now, still, computer needs the signal to be in digital format. So in order to change this sequence of numbers, so the signal will be here numbers 5, 1, -1. It's sequence of numbers, okay? So in order to change this one to 0, 1, okay, 0, 0, digital word. So in order to do that, you need to pass the signal into the encoder. All right. Now here usually xn should be here. Usually we refer to the discrete time and discrete amplitude signal. So here we give it x of t, and at the output of the quantizer we give it the symbol x brackets of n. So n here refers to the integers because you are taking sample at an integer multiple. Okay, usually it's written like this: x of n ts, where ts is the sampling period. Okay. All right. So this is in general, the analog to digital converter. And today we are just working on the sampler. Today we will introduce the sampler and how it works. So sampling and reconstruction. Of course, if you need to read the sampling, you need to know how to reconstruct the signal. So it should be a reversible process. So sampling represent continuous time signal x of t by a sequence of numbers which are the values of x of t. So this sequence of numbers, they are the values of x of t at discrete time instance. And this discrete time instance referred to t equal nts, where ts is the sampling period and n is an integer expressing time position. Let's see this example to understand how the sampling is performed. Let's have this continuous time signal. If you need to plot this continuous time signal, it will be as such. Okay, it's defined for the right-hand side. Now, suppose you need to make sampling with the sampling period 0.5. So you need to take a sample every 0.5 second. You need to take a sample from this continuous time signal, okay, every 0.5 second. So you take a sample, you record this number. So let's say, of course, start at 0, e, you substitute 0 here, e to 0, 1. So at 0, you will have the sample value 10. So let's take at 0.5 second. So you just substitute 0.5 instead of t, and you will get what? 3.68. So you will get the value here at the first ts, 3.68. And then you take another after 0.5 seconds, so you will get at 1 second, you will get this value, and so on. So this, you can see, instead of representing x of t as such, we start representing x of t as sequence of numbers. Look, x and ts. So you take samples at multiple of ts. 0, 1, 2, 3, 4 ts, and so on and so forth, until you sample all the whole signal. So instead of representing a signal in this such expression, continuous time expression, we start representing signal as a sequence of integers. the samples of x of t. So how practically we can do that? The sample of x of t at nts can be obtained by using sampling switch, which closes every t seconds. So what do? Suppose this is the sampler clock. Here you have x of t, continuous time signal, and here it becomes s of t, sample signal. How is that done? Suppose that you have a switch here. This switch will close every ts. Every ts. In doing so you close. When it's open, the output here is 0, let's say 0. When this one close, you will sense the value of x of t and you will have this value. And then if you open the switch, you have 0. Close, you will get a value. Open the switch, you will have 0, and so on and so forth. So here you will have sequence of integers. Sorry, sequence of numbers. And here you have continuous time signal. So this is how you perform then sampling switch. We use sampling switch. So for the sampling process to be useful, right? For the sampling process to be useful, we must be able to show that it is possible to sample in such a way that the signal x of t can be reconstructed from the samples. You cannot just do sampling and you are not sure whether you can reconstruct the signal or not. No, we have to make sure that we can reconstruct the signal. Okay, this is most easily accomplished in the frequency domain. So to decide how we are performing sampling, we need to look at the signal from the frequency domain perspective. So we understand the sampling rate. Okay, how to choose TS. So the important question now, how to choose this TS. Does it affect on the reconstruction of the signal? This is what we ask. Yes, of course. And this is we can be seen from the frequency domain representation. But to imagine this in frequency domain, let's just imagine the sampling, okay, the process of sampling can be seen as a multiplication of x of t by a train of a very short impulses, okay, and we make instantaneous switching. So imagine this is x of t, and here there's a multiplication block. This multiplication multiply the input signal with p of t. P of t is a train of very short pulses. So these impulses, okay, very short pulses, it means impulses. If you multiply this one with this one, this is delta of these shifted at every nts. Okay, if you multiply this one of this one, and we know multiplication of the signal with impulse function, it means you evaluate the signal at the shift value of that impulse function. So x sample can be written as such: multiplication of x of t with a train of pulses. The train of pulses, as I mentioned, can be represented in this summation. This one can be represented mathematically in this expression: summation of impulses shifted at every nts. So P of t is periodic signal. This one, it is periodic signal. All right. Hence, we can find its Fourier series expression. To find the Fourier series expression, we can write in terms of complex exponential Fourier series, and we need to find just the coefficient of pk. Now, to find pk, okay, this is how we find it. We just integrate over a full period of one of the periodic signal, delta of t. And this one, if you just perform the integration, you will get 1 over t, because this is usually is 1. All right, this is 1. So pk equal 1 over t second, which is 1 over second, it's hertz. So back now to substitute this one here. All right, and then I need to perform and find Fourier transform of this signal, which is represented in Fourier series. All right, 1 over ts, it is the same as fs. All right, And from the Fourier tables, the Fourier transform of this signal will give you, this is the frequency translation, if you remember, the property. And this is what we refer to B of F. All right. And one can do it, if you remember, without doing all of that before. We can just use the expression Fourier transform of periodic signal, expression, which we derived in the previous lectures immediately. This is the expression. Okay, you take the Fourier transform of one impulse, which will give you J of F, and you sample J of F at every kf seconds. So this one will give you 1, and you have the same expression immediately. Type. Then what happened so far? We imagine the sampling as a multiplication of a train impulses with the original signal x of t. Type. And this one we have already written, we have found an expression for b of t, and in Fourier in frequency domain as well we have already found. Type. As we know, multiplication in time, if you need to look at it in a frequency domain, it tends to be convolution. Let's do that. So x s of f, okay, we know what is x s of f equal, a convolution between x of f, the original signal, and the Fourier transform of the periodic signal, which is already found here. Here it is. All right. We need to convolve this one with the signal in frequency domain. So this convolution can be conducted as such. It's a linear operator, so you can do it part by part. Okay. So you convolve with the impulse, and we know convolving x of f with an impulse or a signal with an impulse, you just take the value of that signal shifted at this shift, if you remember. So this convolution will return to be as such. So here, what we have found here, the frequency representation of the sampled signal, Jama'ah. So this is the easiest way to imagine it. If you just multiply by a factor with f of s, okay, and a summation of shifted versions of x of f, the original signal. To understand this one clearly, let's look for the plotting. Suppose you have any x of t, and it is a band limited signal. So it is banded, it's limited from, it's limited, sorry. So it's been limited with fp and minus fp. Suppose you have x of t, and this is x of f, suppose. Now in time domain, sampling what is doing, just multiply this signal with a train of impulses. In frequency domain, you just take the Fourier transform of these impulses. We have seen earlier now. It is the same, it's a train of impulses, okay, shifted at every fs, 2 fs, 3 fs. Here it was ts, 2 ts. Here it turns to be the amplitude multiplied with 1 over ts, and the impulses shifted with fs, 2 fs, 3 fs, and so on. Now, in time domain, we performed multiplication. In frequency domain, it tends to be convolution. Let's see what happens. So if you just perform multiplication, you are sensing the value of the signal at every ts. So the signal will be a sequence of numbers, all right? In frequency domain, it is the original spectrum of x of s, x of f, sorry, repeated at every fs, fs. That's it. And just multiplied with 1 over ts ببساطة. هي الأوريجينال الأوريجينال سيجنال بالفريكونسي دومين شو بصير شكلها؟ نفسها ولكن it becomes periodic, repeated at every fs. Okay, periodic. وطبعا بدنا نطلع على الفاكتور المضروبه في الامبليتيود 1 over TS or مضروبه ب FS. هذا ببساطه اللي هو السامبلينج، شكله بالفريكونسي دومين وشكله بالتايم domain. So it's important to note that the above plot is correct if and only if there is no overlap between the different shifted version of x of f. يعني هذا الرسمة صحيحة as long as ما في بينهم overlap، يعني هذه الإجر هذه النقطة ما بتصل هذه النقطة. إذا وصلت بده يكون شكلها هيك. مظبوط؟ وهذا السيناريو المهم بالنسبة لنا إنه إذا وصلت، إذا حتى أنت you need to recover the original signal, what do? You pass this sampled signal هذه through a, let's say, ideal low pass filter, and then you are able to reconstruct the original signal. But if the signal is overlapped, the spectrum is overlapped, you cannot reconstruct the original signal. You have a distortion. All right? You have a distortion. So here we can understand that هاي الإجر كم قيمتها؟ هي FS ناقص FP. FP طبعا highest frequency content in the original signal. So this leg it is FS minus FB، وهذه الإجر FP. متى هذه الإجر لا تصل هذه؟ As long as FB, all right, FB is less than or equal, let's say, FS ناقص FB. Remember, FS sampling rate والFB highest frequency component in the original signal. جيب هاي الFB هون على اليمين تصير 2FB less than or equal FS. إذا ما إيش نفهم هنا يا جماعة؟ هون إحنا طلعنا بالنتيجة اللي بنسأل عنها. sampling rate هذا السامبلينج ريت لازم يكون أكبر أو يساوي ضعف ال highest frequency component of the original signal. كمان مرة. For this signal to be recovered correctly, sampling rate هذا ال FS should be minimum double the highest frequency component of the original signal. All right? Then the spectrum of the sampled continuous signal x of t is composed of spectrum x of t plus the spectrum of x of t translated to each harmonic of the sampling frequency. هذا شكل ال xs of f اللي هو تقدر تكتبه in this expression. Okay. No overlap between the different shifted versions of x of t happens متى no overlap متى ما بصير no overlap happens if really fs minus fb greater than fb. زي ما قلت هون نرجع كمان مرة نذكركم لما تكون هذه النقطة fs minus p greater than fp. fs minus p greater than fb, then there is no overlap. Okay, taking this one here, so fs should be minimum double the highest frequency component of the original signal. Minimum double the highest frequency. إذا TS قديش تكون؟ 1 over TS if you like, greater than 2 على TB, or sorry, 2 FB. alright. إذا بدي TS هنا TS اقلب بصير عندي 1 على، إذا هنا T signal or هون sorry اللي هو 1 على 2 FB. إذا السامبلينج بيريود لازم تكون alright 1 على 2 FP أقل أو يساوي 1 على 2 FP، والFP الهايست فريكونسي كومبوننت الموجود بالسيجنال. إذا given that x of t is a band limited signal، طبعا احنا عرفناها الباند limited signal هيك شكلها. Okay. This means, what does this mean? This means x of f is to be recoverable, from x of s, and consequently x of t from x of s of t. So we can recover x of f from the sampled version as long as sampling frequency greater than the double of the maximum frequency component. All right. Now, what happens? So if f is greater than the double of fb, then we can recover, this is another interpolation, we can recover x of f from xs of f by simple low pass filter with a bandwidth fs over 2. So how we decide that we can reconstruct the original signal with this one? Let's come back to the frequency representation. So in order to recover this signal, the original signal, which has amplitude A and this shape, you need to pass the original signal through a low pass filter, هذا اللو باس فلتر. ريمبر هنا كانت الامبليتيود A، اذا هون بضرب اللو باس فلتر وفي تي اس بيكون الامبليتيود تاعته، وهون باخذ المينيمم الميديا الديستانس اللي بالميدل. ها. So what is the distance from here to here? Fs. From here to here it's Fs. Take the middle point. So Fs over 2. ليش Fs over 2؟ لأنه يا جماعة ما عندنا ايدل فلتر، عندنا براكتيكال فلترز، والبراكتيكال فلترز مش هيك شكلها، شكل الفلترز هيك بتكون مثلا. Alright? So you have to have a gap here. You have to have a gap in order to reconstruct the signal correctly. So the optimum point, we take the filter, the cutoff frequency to be Fs over 2. So we are able here to design a filter to recover the original signal. The dimensions of this low pass filter, the amplitude response equal Ks, will band plateau cutoff frequency Fs over 2 minus Fs over 2. These are the cutoff frequency. So this is how you recover the original signal. So these discussions conclude to the Shannon sampling theorem, which is one of the important theorem in signal processing. What does it say? A band limited signal x of t having no frequency component above fp, so it's limited, let's say. All right, as in the previous example, fp minus fp, or it can have any shape, or like this, minus fp. So it's limited. If it's not limited, what do we do to make it limited? We let it to pass through a low pass filter, as I told you in the beginning of the analog to digital converter. So you make it a band limited here. If it's not band limited here, in order to make it band limited, you let it pass through a low pass filter, so you remove the noise and make it a band limited signal before start sampling. All right, this is what we mean by a band limited signal. Again, a band limited signal having no frequency component above fp, all right, is completely specified by samples that are taken at a uniform rate greater than 2fp. طبعا remember هون uniform rate، ممكن الواحد يعمله مش uniform rate. Okay, adaptive rate. So greater than 2fp hertz. In other words, the time between samples is no greater than اللي هو 1 over 2fp, as I mentioned. If s, okay, greater than 2fp, if you need the sampling period, so ts less than 1 over 2fp, then the sampling period is no greater than 1 over 2fp seconds. The frequency 2FB هذا is known as the Nyquist rate. Is known as the Nyquist rate. So what's Nyquist rate is 2FB. Let's take the following example to understand clearly. Determine the Nyquist rate of the or Nyquist frequency of the following analog signal. So this is sum of cosine analog signal. We can see that the frequency component. So in order to determine TS or F sampling, you need to know the highest frequency component in this signal. So let's investigate. F1 give you 25, 2 by F. So F equal 25. This one will give you 150 hertz. This will give you 50 hertz. Okay. So if you need to plot it, one at 150, one at 50, one at 25. طبعا في عندنا بالنيجاتيف هون بتشوفوا ماينس 25 إذا double sided spectrum. Anyhow, so what's the maximum frequency component? It is 105. So FB will maximum frequency component 150 hertz. All right. So we design our sampler based on that. So Nyquist rate, it is double of maximum frequency component. Then sampling rate يا جماعة should be greater than or equal اللي هو Nyquist rate اللي هو 300 هرتز. طب تي اس كم؟ أقل أو يساوي 1 على 300 seconds. بين سامبل وسامبل لازم تكون أقل من 1 على 300 seconds. Hopefully it's clear. طب السؤال اللي بيطرح نفسه, what happens if we choose the sampling frequency such that we violate the Shannon theorem اللي هو نعمل FS less than 2FB or TS greater than 1 على 2FB. شو بدي يصير؟ or omega S less than 2 omega B. كله نفس المعنى. طيب نرجع لنفس الاكزامبل. افرض انك انت عملت سامبلينج مش ضمن شانون كونسترين, فانت هي عندك اكس اوف اف وانت عملت الاف اس less than 2 اف بي. هذا معناه انه صار تداخل. اوكي, صار تداخل بين السبيكترم اللي هو shifted version of the original spectrum. اذا لو جمعت انت, ما هو هذا summation مظبوط, السبيكترم هذا اكس اوف اس اوف اف اللي هو السميشن, اذا بتجمع هذه مع هذه بتلاقي انه هذا الشكل طلع عندك. طيب لو سالتك السؤال التالي, can you recover this signal? لا, can you recover the original signal by introducing a low pass filter and fs over 2. هي تعال حط low pass filter هون عند fs الكات اوف فريكونسي بتاعته fs over 2 وماينس fs over 2. ف it is clear that you will not be able to recover the original signal. Okay, you will not be able to recover the original signal. And this phenomena, what we call aliasing. This phenomena, it give you aliasing. So aliasing happens when you make a sampling with sampling rate, هذا ال FS sampling rate less than double the maximum frequency component, then you are unable to recover XF from the sampled version XS of F, and accordingly X of T cannot be recovered correctly from the sampled version. So this is what we call aliasing. All right, aliasing happens when you sample with less than the Nyquist rate. So here let's summarize the ideal reconstruction filter, assuming that the signal X of T is sampled at frequency exceeding the Nyquist rate. So there is no overlapping. The ideal reconstruction filter, هذا ideal, remember هذا ideal وفي منه ايش؟ practical. هذا الايديال هذا الترانسفير فانكشن تاعه equal الامبليتيود ريسبونس تي اس وهي الباند ليميت بتاعته. alright, طبعا لازم ياخذ اللينير فيز ريسبونس حتى ما يعمل ديستورشن. اوكي, اذا متذكرين distortion less. اذا بما انه انت عندك السامبل فيرجن, this one if you apply this low pass filter to the sample version, زي ما قلت الكات اوف frequency fs over 2 minus fs over 2. So xf reconstructed will be اللي هي مضروب هذه في هذه. alright ضرب. So you will obtain this reconstructed signal. طبعا إذا كانت fs less than f2b, if you use this ideal filter, you will reconstruct this signal which is not the original signal. طبعا هذا يا جماعة إذا متذكرين هذا المultiplication with the filter in frequency domain. هذا الفلتر لو أنت بدك تاخذ الفريكونسي التايم دومين تاعه بتاخذ اللي هو هذا الشكل. اوكي sync. هذا التايم دومين representation تاعه sync وبنسميه الانتربوليشن function. وهذا اللي بيساعد في استرجاع، يعني واحد ممكن يطلع عليه بالتايم دومين how you can recover it using this interpolation function. طيب ويعطيكم العافية. طبعا عندنا كويز بمحاضرة اليوم كلها اللي هي الانرجي سبيكترم density والسامبلينج انالوج ديجيتال كونفرتر. يعطيكم